Good day, dear colleagues. Today I would like to present our research of morphology and luminescence of particles based on yttrium fluoride for medical usage. Photodynamic therapy is a modern method of cancer treatment. However, today this method is very limited in application because visible light cannot pass through body tissues. Thus, an improved method has been proposed that includes two-compound medicine, which includes photosynthesizer and phosphor. Thus, by acting on X-rays, it becomes possible to influence most of any parts of the body. So now our task is to create a phosphor that meets the following requirements. The phosphor must be excited by X-ray or gamma rays, which can pass through body tissues, emit light in the region with the length wave required to activate the photosynthesizer. Of course, this phosphor must be non-toxic and harmless to the body, and particle size must be no more than 100 nanometers. The best size is around from 50 to 60 nanometers, and it must have hydraulic stability. So the first part of our experiment was to determine the optimal synthesis environment. So we chose three. It is ethylene glycol, water, and ethanol. In all of this media, we could get a necessary phase, which is orthorhombic phase, which is the most stable in case of yttrium fluoride. Since the sample which was synthesized in ethylene glycol has the smallest crystallite size, we chose this medium as the main media for our synthesis. All the samples were synthesized with cerium concentration 2%. However, as you can see from the figure, the sample which was synthesized in ethanol medium has a higher intensity. So ethanol medium is the best medium in case of getting highest intensity. However, in our case, obtaining samples with smallest size is much more important. The second part of our experiment was to determine the optimal concentration of cerium. As you can see from the figure, some samples have unwanted cubic phase of yttrium fluoride, which dramatically influenced on those luminescent spectra. Figure A presents samples to 5 and 6 mole percents, which have the strongest peak around 266 nanometers. However, in case of samples with 1, 3, and 4%, on figure B, the highest peak is 315 nanometers. Thus, we can conclude that cubic phase shifts the spectrum to the longer wavelength. Sample with 5% of cerium has the highest intensity. On the figure C, you can see the graph of decay time of sample with 5% of cerium. In case of photodynamic therapy, the sample with the longest decay time is the best, since it will make duration of X-ray radiation less. On the figure D, you can see X-ray luminescence spectrum of the same sample, which was measured on a laboratory setup with a copper anode at voltage of 80 kilovolts and current of 62 milliamperes. Next part of our experiment was to determine the optimal synthesis duration. A number of samples was synthesized during 6, 8, 12, 16, and 20 hours. The samples were synthesized without cerium. As you can see on the picture, it's possible to obtain the smallest particle size during 4 hours. However, unfortunately, it is impossible to obtain a necessary orthorhombic phase during 4 hours. In this case, the sample will have mix of cubic and orthorhombic phase. However, it is possible to get necessary phase during 16 hours. And the fifth part of our experiment was to determine the optimal stabilizer. In this case, we used polyethylene glycol, polyethylenamine, and polyvinylpyrrolidone. Stabilizers prevent the agglomeration of the particles and ensure their biocompatibility. We used polyethylene glycol with different molar mass, 200, 2000, and 20,000. On the microphotographs AB, you can see a sample with polyethylene glycol 20,000, CD is 2000, and EF is 200. Samples with polyethylene glycol 20,000 and 200,000 have the best size and morphology. If in case of polyethylene glycol, you could see the particle shapes is very close to sphere. In case of polyethylenamine and polyvinylpyrrolidone, you can see particles with sharp edges, which are quite toxic for body. In case of polyethylenamine, which you can see on microphotographs G and H, we couldn't get particle size less than 500 nanometers. And in case of polyvinylpyrrolidone, which you can see on microphotographs I and J, The morphology of the particles are more uniform, however, it still has a lot of sharp edges. In conclusion, the sample with 5% of cerium has the highest intensity. The optimal synthesis duration is more than 16 hours. Ethylene glycol medium was chosen since in this case we can get particles less than 100 nanometers. And to prevent agglomeration of particles and to get the best morphology, polyethylene glycol 20,000 was chosen. Thank you very much for your attention.